All right, we'll go ahead and get started. So hopefully you guys had a little bit of a rest over break. Today is primarily concept stuff. So I feel like that's pretty typical first lecture of a new chapter. We have to kind of like lay the foundation. So just prepare yourself for that. It's kind of a lot of talking, kind of a lot of ideas. And a lot of them, we're tying them. Oh, I forgot to look up what chapter this is. I think it's chapter 6. If someone wants to tell me. I can't remember. No, I think it's 5. 6 feels like it was gases. Anyway, this is referencing back to chapter 5 where we talked about solutions. So mixing usually a solid into a liquid, like salt into water or sugar into water or something like that, to form a homogeneous mixture. Okay, so we're going to delve a little bit deeper into the different types of solutions that we could have, as well as how they form and how we know which things will form a solution or be soluble is the term we use, versus which things are insoluble or won't form a solution. So think of like oil and water, those are going to be insoluble. As much as you shake them up, they're just going to immediately separate. Or something that's soluble like sugar and water. As long as you don't put too much sugar in there, if you mix it up, the sugar will dissolve into the water and it'll all look the same. Okay? So a key point that we didn't talk about back in chapter 5 is that what makes a mixture soluble or makes it homogeneous is the interactions, like actually intermolecular forces between the solute and the solvent. So before, we didn't know about those interactions, so obviously we couldn't talk about them, but you have to have an interaction happening between the solute and solvent in order for it to stick together. So in the case of, we'll use salt water at the beginning of today just because that's one we're really familiar with. So when you have sodium and chlorine dissolving into water, you know, we've drawn this picture a bunch of times. I think there's like a good image of it later on as well. But you get the water surrounding the sodium with its oxygens pointing inwards. Okay, because the oxygens have that partial negative. So I'm going to go ahead and draw that on to remind us. And the sodium has that full positive charge. So that interaction is technically called an ion-dipole interaction. That's what keeps the sodium and chlorines like suspended in the water, okay? So that it's uniform throughout, which is what homogeneous really means, okay? So remember, homogeneous means it's a uniform mixture. Another word we use for that is to say that the two substances, the solute and the solvent, are soluble, or they'll mix. They will mix and form that uniform mixture. And what we really mean by that is that they have interactions, intermolecular forces between them. So solute, solvent forces. We'll say intermolecular, although some of them are ions, not molecules. So what we're going to talk about mostly today is how does the strength of those interactions determine whether or not the thing will mix or not. Like, does the solute and solvent, when it comes together, is that a good, strong force that holds them together? Or is it weak and something that makes them kind of want to separate from each other? So the other thing we're going to talk about in this chapter is other mixtures other than just solids dissolved into a liquid. I feel like maybe we referenced liquids dissolved into a liquid. Like the example they give here is alcohol dissolved into water, specifically ethanol. But that could be any type of alcohol liquid that's dissolved into water. We wouldn't give the example of oil and water because they don't mix with each other, but like if you had, there's lots of additives in gasoline, and those are all nonpolar compounds, so other CH compounds that get mixed into the octane. So that would be another liquid example. Soda is an example of a gas dissolved into water, and those behave really differently as far as how much will dissolve and how it will stay in there. Obviously, you know, if you leave a soda uncapped, it's going to go flat, like all the CO2 is going to come out. But if you keep it capped, there's a good amount that they can force into the liquid. And then gas is something we see really commonly, like just the air surrounding us is a mixture of gases. The one that's probably the least common, or at least hardest for people to understand, is the idea of a solid and a solid mixed together, because they can't be in the solid form when they mix. They're not going to just combine with each other. They have to be first melted and then allowed to re-solidify. So metal alloys are the most common example of a solution where it's a solid and a solid. Okay, so like I said, we're going to talk about what makes them soluble or not. So keep in mind, every time when I say soluble, that means they will form a homogeneous mixture. Okay, so we're focusing a lot now on the energy, because not only have we studied intermolecular forces, but we also studied energy recently. And so we have enough information to really talk about what's going on when we dissolve something into a solvent. Okay, now I'm going to highlight it as like 3 separate steps that this goes through in order to form a solution. They don't really happen individually. They happen all at once, like all 3 of the steps are happening simultaneously. But it's a really good way to model it because it helps us to look at the individual interactions, okay? The pictures on this aren't super helpful, but the diagram itself and how the energy changes is. So the first step, it's written here, but also over there in the picture. The first step is we need to separate the solute particles, okay? So if we're talking about salt water, this would be like we have sodium chloride, and we need to separate it into sodium ions and chlorine ions that are away from each other. So they're not interacting with each other anymore. We're breaking that interaction. Now, if we were to do this not in the presence of water, it's going to be really, really hard. This is basically melting salt, which is like in probably the 1 to 2,000 degrees Celsius that it would require. So it's a lot of energy to break those apart. Remember, anytime we have 2 things attracted to each other, and the primary attractions that things have in chemistry is positive and negative, whether that's a nucleus and an electron, or whether it's 2 ions, or whether it's 2 things that have partial charges. It's all about the positive and negative, right? So we have a positive and a negative that are attracted to each other. Think of like a strong magnet, and we have to pull them apart. That takes energy, right? So that first step, we have to go up in energy to break apart that solute, the sodium chloride. If you look at the picture like on your screen, it, it's like they're all in this organized way, and then they look all kind of chaotic on that side. They're trying to describe it breaking apart. I think just writing sodium chloride, sodium plus chlorine is probably a little bit easier to understand. So this would be specifically for a salt, but we could apply it to any solute. If it was something like sugar, you would actually be breaking apart the sugar molecules from each other. So sugar molecules have a lot of those alcohol groups. So they're, come up here. They're either these there's relatively long chains, or they form in a ring a lot of the time, but they have a lot of alcohol groups sticking off of them. Okay, so because of that, they have hydrogen bonding, and then they hydrogen bond with other sugar molecules. So you'll have one, and then you'll have another come along and have a positive side interact with a negative side, right? The oxygen side is what's going to have that negative charge, and then some of those carbon-hydrogen areas are probably going to have positive charge. But there's going to be an interaction between the sugar molecules, and you're going to be breaking that. That would be another example of solute particles being broken apart. And the sugar molecules are attracted to each other as well. Sugar obviously melts at a lower temperature. I'm trying to think. Melting point is probably somewhere in the upper, like not quite 100, because it melts before. Does it? Actually, I don't know, because I've never made like straight caramel where you caramelize sugar. I don't know. I don't remember what the melting point is. It's in the hundreds of degrees Fahrenheit, though, not thousands, like salt. Okay, so that's the first step, breaking it apart into its individual solute particles. The second step is really similar. It's just the solvent now. So we're breaking the solvent into its individual particles. So you can see the green one is like all ordered, and then up there it's supposed to be all kind of chaotic to describe them being broken apart. So in the case of water, we're talking about there's a bunch of water molecules that are interacting with each other. Water is going to interact with its positive side, interacting with its negative side through hydrogen bonding. So relatively strong force that's holding those water molecules together. And we have to separate those because we have to have a spot to stick the sodium ion or the chlorine ion into. So it's not that we're completely breaking every single interaction. Sometimes we'll describe this as forming holes for the solute particles to slip into. Okay, so just enough so that there's room to take those solute particles and surround them with water. And then the last step is they come together. So the water, in this case, comes together with the sodium, and also some water comes together with the chlorine. So the solute-solvent interaction is what we're talking about now. So that would be this picture we had above. I think it's kind of ways away. I'll just redraw it real quick. So when I'm being lazy, you can draw water just like a little V, where the tip is the oxygen and then the two ends are the hydrogen. So in sodium, the oxygens point towards it, and in chlorine, the hydrogens point towards it. Okay, so those interactions between the water molecule and the ion, so those would be ion dipole interactions. And because that's now two things that are coming together, things that are attracted to each other, that's going to release energy. It takes energy to break apart things that are attracted to each other. So that's the first two steps. We're breaking interactions. That's why we go up in potential energy. And then when they come together, two things that are attracted to each other, that's going to release energy. So that's why we see the energy diagram drop back down. So we give these names, I guess, if you want to call that the amount of energy. So it's a delta H. It's still an enthalpy or potential energy difference. And for the first step, we just say the delta H of the solute, meaning breaking apart the solute. The second step is delta H of the solvent, or breaking apart the solvent. And the third, this is on the picture, I'm just writing it in the text as well, the delta H of mixing them together. So we just say delta H mix. And then the overall difference between those, so, this one takes energy, but this one obviously is releasing more than that. That overall difference is going to be our delta H of solution. So how much overall energy change is there when you form the solution? So take just like 30 seconds and indicate positive or negative for each one of these. 1, 2, 3. So the first two take energy, they should be positive. Last one releases energy, that should be negative. And in this particular example, they're showing us that the delta H of mixing is bigger than the sum of the other two. So I'm just going to give you some rough numbers. Let's pretend like this one's positive 50, this one's positive 50, and maybe this one's negative 120. Okay? In that instance, the overall difference is negative 20, meaning it's going down in potential energy. I mean, you can just picture this like an energy diagram. Think of like reactants and products. Okay? So the reactants are higher in energy than the products are, meaning it's decreasing in potential energy. That's why the delta H would be negative, and we call that exothermic. So still going back to chapter 7 kind of terminologies. And exothermic reactions are always favorable, right? Because things tend to a lower potential energy. If I drop the pencil, if I let go of the pencil, it's going to fall, right? It's going to a lower potential energy. That's not like the complete story. We'll kind of explain a little bit more in a second, but it's certainly a favorable process. Going down in potential energy is a favorable process. Okay? Okay, so let's just, I just basically said all of this stuff on the previous one. So this is comparing step number 3. I'm going to label them as 1, 2, and 3 as we go, but just recognize that we can talk about them in terms of their delta H as well. So when you do this, you're comparing step number 3 to step number 1 and 2. Because 1 and 2 are the things that we know takes energy, and number 3 is the thing that releases energy. So I already said the answers to these questions. I'll just write it down for you. But we said which side of this, either the 3 or the 1 and 2, is larger. Well, we said number 3, or the delta H of mixing, was larger. We could just see that from how they drew it, which meant that the sign overall was negative, which meant, yes, it's a favorable process. And we can actually do this quantitatively. We won't usually see it this specific, but we could represent this if we knew the actual values of all 3 of these steps. We could actually calculate the delta H and determine whether it's exo or endothermic. So in this one, I want you to, it says indicate the sign. I want you to actually like tell me the number, the amount, not just the sign of the delta H solution. And then I also want you to draw an energy diagram. So similar to what we did before, but with this actual data. Draw me an energy diagram and then tell me what the value of the delta H of solution is. Just give you like 2 or 3 minutes to do that. Okay, so obviously this isn't to scale. I was looking at it and I'm like, that is definitely not twice as much as step 2, but whatever. Okay, so the first step, 16.5 kilojoules. So up a bit, it's positive, so we know it's going up. Also, we know that it corresponds to breaking apart interactions, so it's going to increase. Then the second step, 22.8. Now, it doesn't matter if you confuse like step 1 and step 2. It's just breaking apart the solute, breaking apart the solvent. Doesn't matter which order we talk about them in. Typically, for whatever reason, we talk about the solute first, but don't worry if you get those confused. The first 2 steps, so those are the ones that take energy. So altogether, those take 39.3 kilojoules. Because usually we're just comparing, not usually, we are always comparing the first 2 together compared to the last one. So the last one releases, because it's negative, and because they're forming interactions, releases 91.7, which means there's actually, from start to finish, there's an overall drop of 52.4 kilojoules. So again, this one's exothermic. Yes, it's favorable, has a negative sign. Exothermic. And any time we have this we have an exothermic process for dissolving something. This will always make the solution soluble. So like by comparing these numbers, we're basically confirming that the solution will come together and dissolve and form a homogeneous mixture. So if it's exothermic, it will be soluble. Okay, this is as specific as we can get when we have actual numbers and we can calculate what the delta H of the solution is. Remember, that's what we call this part, delta H of the solution. That's as specific as we can get. Now, the rest of class, we're going to go broader. So we're going to talk about the general size of these steps and how we would know how strong or weak those interactions are. And then we'll end with a very broad rule of how to predict if a solute and solvent are going to be soluble. Because that's kind of the whole point of this, is that we want to be able to look at something and predict if solute and solvent will form a solution. Okay, because not everything mixes together, right? Okay, so all of that, whether or not it's going to mix, like I said, is dependent on the interactions that both the mixture has. That's what's drawn in these images down here, would be like the two things mixing together. So this would be the delta H of mixing would be determined by the interactions of the solute and the solvent. And then also breaking apart the interactions between the solute and breaking apart the interactions between the solvent. So they have this other little diagram up here. So you have to break apart the solute. So the red ones are representing the solute. So this is like step number 1. You have to break apart the solvent. That's step number 2. And you have to form the solute solvent. That's step number 3. And the individual strength of each of those steps is what we care about. And the way we know the strength of them is from their intermolecular forces. So the example we gave of salt water, the interactions between the salt, the ions, that's really strong. The interaction between the water particles, the water molecules, that's relatively strong too, right? Those are hydrogen bonds. It's the strongest when we're just talking about molecules. But the interaction between the solute and the solvent is this one, the ion dipole. That's like one of the strongest that we know. So again, just because the two things have strong intermolecular forces, it's okay that we break them apart because the force that they form is even stronger. Just like this would stick with all the examples we've done so far. The force that they form, step number 3, that is stronger than the energy required to break them up. So we've got two little charts here to kind of summarize this. So there's this one up here, and then there's one on the next page. So I'm going to kind of like, oh, that one's not even on this example, so I don't have to do it here. So the one we just did is the first one here. So this is the exothermic one. And the greater than less than sign is showing that the solvent-solute interaction, so step number 3, this is delta H of mixing here. Step number 3 is bigger than the first two, okay? So it's just telling us it releases more energy than it takes. So that will form a solution. But what about if they're kind of similar? So the second line there. What if the solute-solvent interactions, and I'm going to change that to approximately the same, not exactly the same. If they're approximately the same, then a solution will also form. So we'll label that as like, if I can write this in there in that tiny space, slightly exo or endothermic. So they're really close to being about the same. Either it's going to release a little bit or it's going to absorb a little bit, but that's okay. So an energy diagram for that second one would look like maybe you go up, up, and down, and they're pretty much at the same level. Slightly higher, slightly lower, it's okay. Now, it starts to bother some people why it's okay even if it's slightly higher, because that's an increase in potential energy. Why would we see a ball doesn't roll up a hill on its own, right? So in any process, we've only talked about one part about what determines whether a process will occur. So there's the delta H, the enthalpy, but there's also this thing called entropy that we haven't talked about. And we won't get to it in here. I feel like it's not even covered until like chapter 19 or 20 in the textbook. So it's kind of weird that we actually talk about this before we've even had the opportunity to get to talk about entropy. But it is another factor. You don't have to really know anything about it. Just know that it's another factor that affects whether or not a process will happen. And in the case of dissolving something, entropy is always favorable. So always favorable for forming solutions. So in the picture that I've drawn here, where there's a slight increase in potential energy, we would say that the enthalpy is unfavorable. But because this other factor, this entropy thing, is favorable, it kind of compensates for it. Okay? So that's why it's okay to have a slightly endothermic difference in energy. I mean, this shouldn't be that shocking because there are other chemical reactions that are endothermic that still happen. We just haven't given you the whole story of why that's okay, because the ball doesn't roll up the hill. So I've never really thought about gravity and how entropy plays into gravity, but I guess in the case of entropy, or in the case of gravity, entropy is probably always unfavorable. So it's like completely reliant on potential energy. In this process, though, the entropy kind of helps move things along. So it's okay if the potential energy increases a little bit because that other factor is always favorable. Okay, so that's why I did this like approximately for the middle one, because it doesn't have to be exactly equal. It's going to be approximately. So the last one is saying that steps 1 and 2 are greater than step 3. Now it does say depending on relative size, but let's just say, we'll scratch that out because we talked about that earlier. If you've got, so I'm going to redraw our picture here. They're saying that steps 1 and 2 are bigger. Like clearly they're larger than number 3. Meaning that number 3 must have not had very strong interactions. So maybe that's like dispersion forces or something. So in that instance, when it's highly endothermic, and I realize how endothermic is highly endothermic, it doesn't matter. If it's a little bit endothermic, that's okay. If it's a lot endothermic, that's not okay. So in this instance, a lot endothermic, it's not going to form a solution. We would say it's insoluble. And again, the size of those steps is dependent on the interactions. So on the next page, I have 3 examples. They're different than the earlier ones we've encountered, but 3 examples that give like relative strength of the interactions. So if you had, so this is step 1, 2, and 3. So in solution A, if you had relatively weak interactions for the solute and solvent, it's not a big deal to break them apart if there's a really strong interaction when they come together, the solute and solvent. So in that case, it would be soluble because that strong interaction kind of drives them together to form a solution. You can draw like a little energy diagram for this too. So the first 2 steps are relatively small, but the last one is big. So you get a release of energy there. So B and C, a little bit different. So it says the first one's weak, the second one is strong, and then the last one is strong. Well, that's going to depend on how strong is strong and how strong is weak. This is why you really have to rely on the amount of that delta H of solution. So we would have to have more information about that. We would have to have a little bit more concrete data about how strong or are those interactions. But we're always comparing step 1 and 2 together to step 3. And then in the last example, we're saying takes a lot of energy to break them apart, but it doesn't release a whole ton of energy. And that's when it's going to be insoluble. So this comes up in 2 slides. I thought it was the next one. Unfortunately, it's not. In 2 slides, I have the solubility rules that we used in chapter 5. Those are interesting because those are salts. They're ionic compounds, and we're saying, are they soluble in water? Well, we just did the sodium chloride example and said, oh yeah, it takes a lot of energy to break sodium apart. Like this would be an example of that. It's a strong solute-solute interaction. It takes a lot of energy to break the water apart. Okay, solvent-solvent interaction. But in the case of sodium chloride, it releases a lot of energy too. So that's why that one in particular. Some salts, they're really strong interactions, and the interaction between the water and the ion might not be enough to compensate for how strong those interactions are. Salts are just weird, and especially the strength of that ionic bond varies a lot. And so it's just too hard to predict. So for ionic compounds in water, that's why we have to have the solubility rules to know whether or not it's going to be soluble or not. We can't just rely on the strength of the interactions, okay? Because there's just too much variance. Okay, so now we're going to get even broader, and we're going to come up with this rule that we can actually apply to pretty much everything. It's going to work, and it's going to give us a good idea. And in reality, when it comes down to it, some of these things, we just have to mix them in a laboratory setting and figure out if they're soluble or not. Because generally, we don't have that data, that actual numbers to calculate each one of these steps. But once we do it, and once we figure out whether they're soluble or not in each other, then we know something about the size of those delta H's. So the easy way, and the way we're going to rely on from now on, is called like dissolves like. And really, you just have to look at the polarity, and things that have similar polarity tend to dissolve in each other, and things that don't have similar polarity won't. Okay? So the first two, either if they're both nonpolar, or both meaning solvent and solute, or if they're both polar, then we would say that they will dissolve in each other. Now, we do group ionic typically as something that's polar, but like I said, you got to look at the solubility rules when you're talking about ionics, because there's just too much variability. Okay, so we are going to have to use these again. If you didn't take Chem 1 from me, these are similar to the one that's in the textbook. I just kind of summarize them, I think, a little bit more clearly. So on the homework, you'll have enough practice where it'll give you an ionic compound. And in that instance, you can't just use like dissolves like. You have to use the solubility rules. So you'll want to practice using those solubility rules again. Okay, then if you have things that are different, like something that's polar and nonpolar, for example, water and oil. So water is polar, but oil or gasoline or something is not. Those will not mix. And what it really comes down to is that the interaction between the water and the gasoline is not strong enough to overcome the fact that it took a lot to break the water apart. Okay, so like in this particular example, it takes not very much to break the gasoline apart, but it takes quite a bit to break the water apart, and then not a whole ton is released comparatively. Maybe I should draw that a little smaller. Not a whole ton is released when the gasoline and the water come together. Now in this particular picture, they use pentane, which is close enough to octane. I just wanted to use something you guys would be familiar with, because you're probably not familiar with pentane. Okay, so polar and polar would be something more like water and alcohol, right? Alcohol has that OH group, and so it's polar. It actually can do hydrogen bonding, and so it interacts very well with water. That would be polar and polar. Or nonpolar and nonpolar would be like all of the additives that they put into gasoline. Those would be the solutes. Those are all nonpolar compounds too. So they're all these CH compounds. In fact, there's probably some pentane in the gasoline too. Well, maybe not if they didn't do a very good job. So there are a lot of CH compounds varying in size, but they're nonpolar and they will dissolve in the nonpolar gasoline. Okay, so we're gonna apply this here. We'll do this one together, and then on Wednesday, I'll have you guys do this one with vitamins that I always think is fun. Okay, which of the pairs of compounds below are most likely to form a solution? So using the idea of like dissolves like, we want to basically find which one has similar polarity, which ones are either both polar or both nonpolar. So I'm going to color code these. Pink is polar. Ammonia, NH3, we've seen that a bunch of times before. The lone pair on the nitrogen is what makes it polar. It makes that trigonal pyramidal shape. So that's polar. Remember, carbons and hydrogens, if it's just carbon and hydrogen, it's nonpolar. Okay? Those two are not going to mix. One's polar, one's nonpolar. Nope, those aren't going to form a solution. Water is polar and ammonia is polar. Okay, that guy's going to form a solution. Polar and polar. I don't know why. That looks like an X. It was supposed to be a star. Will form solution. We can look at the other ones, but we've already kind of found our answer. Sodium chloride, like I said, even though it's not polar, it's like an extreme version of polar. So we would still label that as polar when we're talking about it. CH compound, pentane, nonpolar. Okay, not going to form a solution. Last one, heptane, CH, nope. And then finally, this acetonitrile. You could draw this out. Pretty much since you have that nitrogen, you can guarantee that that's going to have polarity. You've got that nitrogen on the end, nothing else to balance it out. You've got that lone pair, and then you have this other group over there, that carbon with different electronegativity. So that one is going to be polar. Okay, so water and ammonia there are the only ones that form a solution. Debating. I think we'll do this one and leave the next for... Okay, so last thing. Toluene is not soluble in water. Okay, what does that tell us? Water is polar. We know that. So if toluene, this random thing, we don't know what it is yet, is not soluble in water, that must be nonpolar. And then it says which one's the most likely formula for toluene. So we're looking for something that's nonpolar. Well, 3 of those compounds have oxygen in them. And we know that oxygen makes those molecules polar. So this is the only one that could possibly be our answer, the only thing that's nonpolar. All of the others are probably going to dissolve in water. Okay, so we'll keep going with this idea on Wednesday. And then we'll totally take a turn and do a bunch of math stuff too. All right, see you then.